In this video, we are going to go over the answer key for problem set 5. Now, you may have noticed that this problem set looks a little bit different from other ones that we have covered up to this point in this semester. And that's because we are transitioning into Unit 2, which covers inferential statistics rather than descriptive statistics, which is what we covered in Unit 1 in chapters 1 through 4. With the start of chapter 5, we are introduced to the concept of the normal distribution and z-scores. And so with question 1, we are asked to, in your own words, describe the normal distribution and explain how it relates to the empirical rule. And there are a couple of key elements that I'd really like you to touch on here. The first is about the shape of the normal distribution itself. So the normal distribution is a symmetric bell-shaped curve that represents how data values are spread around the mean in many naturally occurring data sets. So what do I mean by a symmetric bell-shaped curve? Well, if you take a look at the image below, this blue line represents that bell and symmetric curve. What does this mean? A couple of things. We know that the majority of our observations here are clustered in the middle and that our mean is going to be at our center point here. The symmetrical element means that it is going to be identical on both sides. So if this was on a sheet of paper and we folded it in half, the values would be identical on both the negative end of our distribution and the positive end of our distribution. The second element is that most of these values cluster around the mean, and the probabilities for these values further away from the mean decrease equally in both directions. So this does relate a little bit back to our symmetrical element that we just talked about here. And so again, our mean is right here at our center point, and the probability of having a value standard deviations away from our mean decrease equally as we move further and further away. And so we know that our mean is our average, and the further away we get away from our average values, the less likely or the less probable we are to have an observation that may be a value further away from that. And so simply what that point is saying is that if we were to get a value either that is significantly less than that or significantly more than our mean value, more than 3 negative standard deviations away from our mean, or more than 3 positive standard deviations from our mean, it's likely an outlier, right? It's falling way outside of what we would expect to see happen within the context of a normal distribution. The last key element of the normal distribution is not only is the mean at our center point here, but so is our median and mode. And so all 3 measures of central tendency are located right in the middle of our normal distribution, and they are all equal in value as well. So how do all of these ideas relate to the empirical rule? The empirical rule itself describes specific percentages of data that fall within certain distances from the mean in a normal distribution. And so this allows us to quickly estimate how data is distributed without having to calculate exact probabilities. So that's that connection here. It basically gives us a roadmap of what percentages we could expect within certain standard deviations away from the mean and what those percentages actually are. So we could expect that approximately 68% of our data falls within 1 standard deviation of our mean value. But this is within the negative end of our distribution and the positive end. So you can see it's going in both directions here. That's why I have a positive standard deviation here on the top and a negative standard deviation. We would also expect that approximately 95% of our values are going to fall within 2 standard deviations of our mean. And so you can see this area is widening even further here. And lastly, we would expect approximately 99.7% of our observations or values to fall within 3 standard deviations of our mean within the context of a normal distribution. So that's the vast majority, obviously, nearly 100%, but we're still accounting for the fact that it is possible that a value could fall more than 3 negative standard deviations away, or more than 3 positive standard deviations away. It's still possible, it's just not very probable. And so if you have any questions about the normal distribution itself after looking at this particular example, please reach out to me because this is really going to be the basis of a lot of our discussions moving well past chapter 5. So I really want to make sure that you have a firm grasp on this concept in particular. Moving on to question 2. This is really building off of our discussion that we just had about the normal distribution and specifically the empirical rule. So let's read this one together. Among individuals arrested for misdemeanor theft, the average age at first arrest is 22 years old. Assuming a standard deviation of 3 years and a normal distribution, what range of ages would you expect 95% of first-time arrestees to fall within? You must show your work to receive full credit. And so if we use this concept of the empirical rule above, because we know we are working with a normal distribution, and we know that we're looking at 95%, if we go back up here, we know that a 95% correlates with 2 standard deviations away from our mean value. We know that the average age of first arrest here is 22 years old, and we're curious about 2 standard deviations away from the mean. We also know that the standard deviation itself is 3 years. So if we were to plot this out similarly on a x-axis here, we would have 22 in the middle. Then we would just subtract 3 to get 19, subtract 3 again to get 16. So we're 2 standard deviations away. Then we'd add 3 and add 3 to get our upper limit. If you look at the math here, you wouldn't even have to necessarily plot it out if you just wanted to do it more quickly this way. And so our upper bound here is 28 years old on the positive end of our distribution and 16 years old. In other words, how we would interpret this within the context of the problem is we would expect 95% of individuals arrested for misdemeanor theft at first arrest to be between the ages of 16 to 28 years old. So relating this back to the idea of the empirical rule, this is a really quick way that we can apply that concept of the normal distribution and the empirical rule to quickly assess how we would expect these ranges to be applicable here, right? It didn't take us a lot of work, and we were able to use this percentage here quickly without having to acknowledge the z-distribution table, standard normal table, and we just had to use our knowledge of the empirical rule to quickly solve this. And so that's one of the beauties of the empirical rule itself, is that it allows us to do quick calculations like this. Moving on to question 3. This was certainly the question out of the 3 that gave folks the most trouble, and I'm not necessarily surprised by this. Obviously, the first question is just more definition-based, and the second question involves just a quick calculation. And so there are certainly a lot of areas here where you could go wrong. And so this one has quite a few steps that we'll work through together. And another point here is I really want to make sure that everyone reads this question carefully, because many of you did not, frankly, in this point. And I don't want you to leave any points on the table, especially if there's an upcoming problem set that may be a little bit of a longer question like this, or especially on a quiz, because I want to make sure that you get all the points that you deserve. And so let's take a look at what question 3 is specifically asking us to answer here. Assume that the distributions of SAT and ACT scores are normally distributed, where the SAT mean equals 1,083 with a standard deviation of 194 and an ACT mean of 20.8 with a standard deviation of 4.8. Calculate the corresponding z-scores and the percentage of the area above and below the normal curve. Based on your calculations, which exam score should Jeremy and Aaron submit with their university materials? Fill out the table below. You must show your work to receive full credit. So definitely the element within the directions itself that was most missed was this statement here. Based on your calculations, which exam score should Jeremy and Aaron submit with their university materials? So there were many of you who filled out the table and followed this direction, but didn't actually use what you found out in the table to answer the question right before it. And so I want to make sure that that's clear moving forward. So just make sure to read these types of questions carefully so that you're not leaving any points on the table. All right, so the first thing that we need to do in order to answer a question like this is first calculate a z-score. I want to take a step back for a moment here and explain what a z-score allows us to do here. A z-score is a measure that is really standardizing in nature. And because we know that the ACT and the SAT are scored along two separate continuums, right? The ACT is on a measure of 0 to 36, and the ACT can go all the way up to a score of 1600. Those aren't compatible easily in our minds, right? And so we need to figure out which one we should actually submit, knowing that they're on completely different scales. The z-score allows us to standardize these units and figure out how well we did relative to each other without having completely different scales in mind. So let's take a look at both Jeremy and Aaron's score here. We see from the question itself that Jeremy scored a 25 and Aaron scored a 23. So obviously this is the answer key, so our answers are already up here, but I want to show you the actual work, which is here below. To calculate a z-score, you need to take y, which is the observation itself, so either 25 for Jeremy or 23 for Aaron, subtract that by the mean score, which is what we can pull from the question itself up here, and divide that by the standard deviation, which we will also pull from the question itself up here. So for Jeremy, his ACT z-score is 25, subtracted by 20.8, because I see that the ACT mean is listed here, divided by 4.8, because that's the standard deviation listed here as well, equals 0.875. You'll notice that the standard normal table or z-distribution table that is posted to Canvas only uses z-scores that are rounded to the hundredths place. And because of that, I will always be rounding my final z-scores when I am calculating percentage areas above or below a z-score to the hundredths place so that I can accurately and effectively use this table. And so because this score has a thousandths place of 5, I need to round up to 0.88. So Jeremy's z-score is 0.88. Let's move on to Aaron's z-score first before determining this element here. Aaron's z-score, he scored a 23. This information is going to remain identical. And so he receives a z-score value of 0.46. So that's where I have that listed in the table as well. Now, this next part can be a little bit tricky, so I want to take a step back and make sure that I'm explaining this thoroughly because this is certainly the area where folks had the most trouble. So a couple of things here. Percentage area above their scores and percentage area below their scores. There's a couple ways we can check ourselves without doing any of the math here first. The first key here is knowing whether or not Jeremy and Aaron scored above the mean or average score. So if we take a look, we see that the ACT mean is 20.8. Jeremy scored a 25 and Aaron scored a 23. So they are both above average. And we know that our mean and average score is always going to be at this center point of our distribution. So they're both on our positive end here, right? They're both above average. They're going to be on this end over here. Because of that, we know that the percentage of test takers that are going to be below their scores is going to be greater than those that did better than them because they are above average. We know because it's a symmetrical distribution, right? 50% of test takers are going to be below the mean and 50% of test takers are going to be above the mean. And since they're going to be above average, they're going to be at least better than the 50% that did worse than average. And they are going to be better than the test takers that did a little bit better than above average, but still worse than their score. And so if you had these switched for whatever reason, that's an easy way to check yourself. We know that the area below for both Jeremy and Aaron has to be greater than the areas above. In other words, we know that the areas above, or the amount of test takers that did better than them, is smaller, right? Because they did above average. You can think of it either way if that's helpful for you. So to calculate these, if you go to the standard normal table, and the expectation for any upcoming problem sets and quizzes is that you are using the one that is posted to Canvas. That is the standard one for the class, and that is the one I will be using to grade moving forward on problem sets and quizzes. So that's what's plugged into Canvas. Let's take a look here. For Jeremy, the corresponding z-value for 0.88, let's take a look at the area beyond z. What you're seeing up here, I took directly off of the standard normal table from Canvas. It's right there at the very top of page 1. This simply explains how to operate the standard normal table and the z distribution table. So let's take a look. We are in a situation here where we know Jeremy scored above average. So let's take a look at this left-hand graph for now, because it'll be more helpful for us in this context. Jeremy's area of beyond Z is going to represent area C. So take a look at those two corresponding values here. Therefore, we know that area C is going to represent the proportion of test takers that did better than Jeremy, because those are the folks on the positive end that did better than him. More standard deviations greater than the mean. They're on the positive end of the distribution. So they scored better than a score of 25. If it's helpful for you to plot this out on an x-axis alongside the normal distribution here on the bottom, go ahead and do that. You can even plot out that the average score on the ACT is a 20.8 and that Jeremy's over here with a 25, but we know it scores all the way up to a 36. It's not likely that you're going to get a 36, and very few people do, but we know that that's the end of our distribution here. So there are people that scored between a 25 and 36, and those individuals represent a proportion value of 0.1894, or we know from earlier chapters, we can easily convert that into a percentage, which is what I'm asking you to do here. We simply multiply our proportion value by 100 to get 18.94. So how we could interpret this within the context of the problem is that 18.94% of test takers scored better than Jeremy on the ACT. How we can quickly determine how many individuals did worse than Jeremy, or rather the percentage of test takers that did worse, is going back to other questions that we had in question 1 of this very problem set, and the idea of the normal distribution as a whole. We know that the entire area under the curve has to equal a proportion value of 1 or a percentage area of 100%. And since we know area C here, we can take the value knowing that this entire area has to be 100 and just subtract this value of 18.94. So if I take 100% minus 18.94, I get 81.06%. If you want to check your math on that, feel free to go ahead. 18.94 plus 81.06 is 100%. So we're covering that entire area of the curve. Another easy way to check yourself. And so a couple of you neglected this area here. So the individuals that tested worse than average, so you weren't accounting for this 0.5 area here. So just make sure, again, to double check yourself that whatever areas you are calculating here has to equate to 100%. Now let's repeat these steps, but for Aaron here. We figured out that his z-score corresponds to a value of 0.46. I have gone ahead and worked out the math down here, if that's helpful for you. I've taken this directly from our standard normal table from Canvas as well. The corresponding area beyond Z, or this C area here, which again, we know is the proportion, and we'll convert it to a percentage of test takers that scored higher than Aaron, or in other words, scored higher than a 23 on the ACT, is 0.3228. If we convert that to a percentage, it's 32.28%. So we can go ahead and plug that into our percentage area above, and we can quickly calculate what percentage of test takers scored worse than a 23 by taking 100%, again, our entire area under the curve, subtracting it by our value of test takers that did better than Aaron to get 67.72%. If you'd like to check your math on that, simply add these two values together and they equate to 100%. And so now we have completed this section of the problem, which is calculating the z-score in the percentage area above and percentage area below Jeremy and Aaron's ACT score. But we still have to do this for the SAT score because this is going to allow us to now compare these test scores to one another. So it's basically just repeating the same steps, but we're using different values now. We can see that the SAT scores are much greater than the 25 and 23 that Jeremy and Aaron scored in the ACT. And so the averages and standard deviations look a little bit different too. Keeping in mind our z-score formula here, we take the observation itself, so the SAT scores were given here, subtract that by the average, which is given to us in the problem itself above in question 3, and divide that by the standard deviation. So Jeremy scored a 1310 on his ACT. Up here in the average, we see that the SAT mean is a 1083 and the standard deviation is a 194. So I'll go ahead and, getting ahead of myself here, and plug those in right here to get a z-score of 1.17. Let's go ahead and do that for Aaron as well, as long as we're here, because we know these values aren't changing. His SAT score was an 1190, so we plug those in to get a z-score of 0.55. So again, we are standardizing these units. What a z-score represents in practice now is how many standard deviations they are either above or below the mean. So let's take Aaron here, for example. 0.55 means that he is 0.55 standard deviations above the mean. We'll illustrate this below on the standard normal curve itself when we have to make our decision, but just keep that in mind. That's essentially what we're doing here is we have now converted this score into a standardized unit of standard deviations. All right, so now we're able to go ahead and fill this part of our table out. And we can now go ahead and calculate our percentage area above and percentage area below. So same steps that we did for the ACT above. I went ahead and screenshotted here the corresponding area for a z-score of 1.17. Again, we know that they did better than the average test taker. Both Jeremy and Aaron did because we know that the average was a 1083. Both of them are above that. And so a couple of things here. We know that the z-score should be positive because we're above that. They are above average. If they would have scored below average, we would expect the z-score to be negative. So that's another quick way you can check yourself. Along with that, because we know that it is positive, we can go back up here if it's helpful for you to visualize this and know that area C is going to be that area of test takers that scored better than them. So in other words, the percentage of test takers that scored better than a 1310 or higher than Jeremy is 12.1% of test takers. So I simply converted this proportion area from our standard normal table and converted that into a percentage. And since we know the entire area under the curve has to equate to 100%, I took 100%, subtracted that by 12.1 to get 87.9%. So I went ahead and filled that out here as well. Same steps for Aaron. The corresponding values for the area beyond Z or area C for a z-score of 0.55 is 0.2912. which is corresponding to a percentage value of 29.12%. And if I take that 100% and subtract it by that value, I get 70.88%. So for Aaron, we know that 70.88% of test takers scored worse than them. That's kind of how you can use this table to interpret this within the context of the problem. You can use it either way. You can either say that 29.12% of test takers scored higher than Aaron, or in other words, higher than a score of 1190, or you could say that 70.88% of test takers scored worse than Aaron, or worse than a score of 1190. So many of you made it to this stage. You filled out the table. But again, this question now is asking us that based on our calculations, which one should they actually submit? So this is now using those calculations to make a decision. We have to inform them, now that we've standardized these units, how can we actually use statistics to make a call? That's what I'm illustrating down here. Using our tables that we calculated before, there's a couple of ways that we can make this decision. Either one, I'm going to show you two ways, is perfectly fine, whichever you're more comfortable with, but I'm going to illustrate them both so you can see how it's done. The first is we can simply compare z-scores. Remember that z-scores tell us how many standard deviations a score is above or below the mean. In this case, the higher the z-score, the better Aaron and Jeremy did relative to the average test taker. We want them to score better, right? Because that means they did a better score. It's going to increase their chances probably of getting into college. So the higher the score, the better here. So let's first take a look at Aaron. We want to inform him whether he should be submitting his ACT or SAT score. I have copy and pasted down here both of his z-scores. And remember, since the z-scores are telling us how many standard deviations he is above the mean, because we know he did above average, what I've done here is gone ahead and plotted them. Remember, our zero value here is representing our mean value. ACT, he scored 0.46 standard deviations above the mean. But on the SAT, he scored 0.55 standard deviations above the mean. And these are standardized units now. So essentially, we've taken away both of those scales since it doesn't make sense for us to compare them. They're apples and oranges. They were on completely different planets for the sake of our question here. But now that we have these standardized, we can now make a call for Aaron and say, hey, you've actually scored higher on the SAT relative to the ACT because you're further along in terms of these standard deviations relative to the ACT here. And so for Aaron, he should submit his SAT score. For Jeremy, he scored a little bit higher than Aaron on both the SAT and ACT, but he needs to make a decision as well. So I've gone ahead and transferred both his z-scores down here so we can visualize this a little bit easier. So we have his ACT score here with this first blue line and his SAT score here with the second blue line. His SAT z-score was 1.17 and his ACT z-score was 0.88. Again, a higher z-score in this case is better because that means you're further away from average. So you've scored higher than the average test taker, which in this case is a good thing. So for Jeremy, since he scored 1.17 standard deviations above the mean on the SAT, while only 0.88 standard deviations above the mean on the ACT, he should also submit his SAT score because the SAT score is more standard deviations above the mean relative to his ACT score. So in this case, now that we've standardized these units, if you were to just look at the z-scores itself, if it's quicker for you to do that and you're able to interpret that in your head, go ahead and use z-scores because again, it's standardized units now and it allows us to quickly make decisions like this. So in other words, both Aaron and Jeremy should be submitting their SAT scores with their college materials. There is also another way you could go about this though, and we'll go over this approach here. We can also use that second half of the table and we can compare the percentage areas above and below the z-score. We know that Jeremy scored better than 87.9% of test takers on the SAT, meaning only 12.1% of test takers did better than him. We can also compare this to the percentage of test takers he did better and worse than on the ACT. So if it's more helpful for you to visualize it this way, then go ahead and do so. It's representing the same thing as the Z-score, but I know some people work better with percentages and visually like this, so it's doing the same thing. So whichever one works better for you. On the ACT, Jeremy scored better than 81.06% of test takers. So all of these folks over there. But we also know that 18.94% did better than Jeremy. And so now we can compare essentially these two areas here. We want to know how many people did worse than him and how many people did better than him. And in this case, it's pretty easy for us to tell. We want the one that he did better on. And for Jeremy, only 12.1% of test takers did better than him on the SAT, where almost 20% did better than him on the ACT. So for Jeremy, you can also relate this in the terms of percentiles. We haven't exactly covered that, but it's a pretty similar and analogous term to percentages. So another way to interpret this is that Jeremy wants to submit the score he did better than relative to other test takers. And because he scored in the 87.9 percentile on the SAT and only the 81.06 percentile on the ACT, Jeremy should submit his SAT score. So again, if it's visually easier for you to interpret these different percentages along the normal curve like this, go ahead and do so. Same idea here with Aaron. We know that Aaron scored better than 70.88% of test takers on the ACT, meaning 29.12% of test takers did better than him. And now if we take a look at the ACT, 67.72 did worse than him, and 32.28% did better than him. So if we look at these percentages relative to each other, we want to see which percentage he wants to submit. And that would be the fewest that did better than him, because that means he scored higher. And that is also the AC or the SAT, I should say, in this case. And so Aaron wants to submit the score he did better than relative to other test takers. And because he scored in the 70th.88 percentile on the SAT and only the 67.72 percentile on the ACT, Aaron should submit his SAT score. So this area is smaller than this, if you're able to visualize it like this. And so if this was shaded, you would see that the percentage of test takers that did better than him is smaller than this one below. And so that's a good thing, right? He wants to be in that more exclusive category of test takers in that really small group that is above the mean. And so, like I said, whichever way is easier for you, if you're just comparing Z-scores, I personally think it's just quicker to see how many standard deviations you are above the mean. That's perfectly fine. But if it's visually easier for you to just compare these percentages, have at it. You can even just take a look at these tables as well. If it's easier for you to take a look at it within this context as well, you can even go ahead and copy and paste this table to this one. It'll be easier to compare the two of them together as well. As I had mentioned, though, using the standard normal table and the Z-distribution table is going to be crucial moving forward. This, unfortunately, is not going away for the rest of the semester and is actually a critical building stone that we will be using for confidence intervals and hypothesis testing, which is really what we'll be getting into for the duration of the semester. And so if you are struggling with this material, please reach out to me, whether you would like to meet individually or stop by my drop-in hours. I really want to ensure that you have this foundation set because, like I said, it's going to be that building block for us the rest of the semester. And especially if you're finding it difficult to use a standard normal table, I am more than happy to sit down with you and explain that if you're finding trouble with that. And so please just shoot me an email. I am more than happy to sit down with you. And as always, I will see you in the next video.